In this video, we're going to discuss curvature and torsion. These are two quantities that are defined for a curve for all values of t. And we're going to discuss the Frenet-Serrat equations and how those are related to the Frenet frame and the equations for torsion. So basically this video is about interpreting curvature and torsion. I'm not so interested in proofs. I don't need you to know where all of these formulas come from, but I do need you to know how to interpret these values. If I give you a curvature and I give you a torsion, I want you to be able to tell me what they mean. So that's your goal when watching these videos, is to be able to interpret curvature and torsion. So let's review a couple of things. So let's say we're in three-dimensional space. Wow. And we're on a curve, C. So maybe it looks like that. And C is given by R of t, and R of t has components, x of t, y of t, and z of t. Now remember how this works. R of t is a vector. It points to a particular location. So it starts at the origin and it points here. And at that point, this is R of t. It says you are here at this location. That's x of t, y of t, z of t. Now if I want a tangent vector to the curve in the direction of motion, excuse me, all I have to do is take the derivative. It's just like Calc 1. The derivative is associated with the tangent. Now, we also think of this differently. If R of t is giving you the position at time t, we can think of this geometrically as a tangent vector, or we can think of this in terms of motion. If this is position at time t, this tangent vector is the velocity at time t. Now we said in another video, an earlier video, that if we want the unit tangent vector, so that is a unit vector that's tangent to the curve and it's 1 unit long, we call that t hat, and that's just r prime divided by the magnitude of r prime. Now if we're thinking in terms of motion, r prime is velocity, and so this is velocity divided by the magnitude of velocity, or if you prefer, velocity divided by the speed. So this is giving us direction. It's telling us the unit vector and the direction we're going along the curve. So if this is our curve, our unit tangent might look something like that. Because at that moment, at that time, that's exactly the direction that we're going at time t. So I'm going to say unit vector in the direction of motion. Now also in another video, we talked about the fact that since the magnitude of t hat is constant, since it's always 1 because it's a unit vector, there is a fact that we know t hat and its derivative have to have a 0 dot product. And of course this can be interpreted geometrically. This says that t hat and its derivative are orthogonal to each other. So if t hat points this way, and a moment later t hat is going to be pointing that way because maybe we're turning in that direction, the derivative is going to point in the direction that we're turning. It meets t hat at a 90-degree angle and it looks like that. Excuse me. Now that may or may not be 1 unit long. So if I want to make it 1 unit long, I divide it by its magnitude. We call that the principal unit normal vector. Now t hat prime points in the direction that we're turning. So if we're turning this way, that's where it's going to turn. The unit normal points in the same direction, but it's 1 unit long. Now it looks like this is less than 1 unit long from my picture. Don't worry about those magnitudes. Just know that this is 1 unit long and this is 1 unit long. So whatever the magnitude of this is, I'm going to take it and I'm going to divide by it, and that's n hat. So this is the unit vector in the direction that we're turning. So if this is my unit tangent, I'm turning this way, my unit normal is going to point down like this. And those meet at a 90-degree angle. Now the binormal vector is orthogonal to both of these guys. It's just b hat, or it's denoted by b hat, and it's given by t hat crossed with n hat. So this is, since these are unit vectors, their cross product is also a unit vector. So b hat is a unit vector. So this is the unit vector orthogonal to the plane containing t hat and n hat. And remember, the acceleration vector is a combination, it's a linear combination of t hat and n hat. So part of the acceleration is pointing in the direction of motion, part of the acceleration is pointing in the direction we're turning. When you put those together, you get the whole acceleration vector. So this binormal vector is the normal vector to the plane containing that acceleration vector. So I guess we were saying it's the plane containing these guys, which means it's also the plane containing the acceleration vector. Okay, so it looks like this. There's t hat, there's n hat. Then by the right hand rule, I put my fingers toward t hat, I curl them towards n hat. Because of the way I've drawn this picture, b hat is going into the page. By the right hand rule, my thumb is going to go into the page, so b hat is going into the page. Now here is just some notation that people tend to use in physics. If they're talking about a vector that's pointing out of the page, they do this. It's like you've got an arrow like pointing directly at you, like my pen is pointing at the camera right now. All you see is the dot, so this is going out of the page. And then if you have an arrow, I don't remember what those things are called. My students in 2 classes have told me what they're called. But the back of the arrow, there are those little things coming off the back. That's what you would see if the arrow was going into the page. So in this picture, using my right hand, t hat goes this way, n hat goes this way, so my thumb is going into the page. So at this point, b hat is going into the page. Okay, now at every point along that curve, you've got a little moving reference frame. It looks like this. That's the Frenet frame. Now from the perspective of a particle traveling along the curve, t hat kind of acts like the positive x-axis, n hat kind of acts like the positive y-axis, and b hat acts like the z-axis. These are perpendicular to each other. T hat points in the direction that that particle is going as it travels along the curve. N hat is always to the particle's left. Now, if you say, well, what if n hat was to the right? That would be fine, but then b hat would be pointing down instead of pointing up. Since we have a right-handed reference frame, n hat, the direction we're turning relative to b hat and t hat, is always going to be to the left. And then b hat is perpendicular to the plane containing these two vectors. So we've got a plane down here. Excuse me. And b hat is perpendicular to that. Now, I just said this out loud, but I did not write it on my paper, so I just want to rewrite that on my paper. The Frenet frame is a set of 3 mutually orthogonal unit vectors. And it provides a local reference frame for a particle traveling along the curve. So we're interpreting these as the direction that we're going, the direction we're turning, and then the acceleration vector is down here somewhere. The binormal is perpendicular to that plane containing the acceleration vector. Now this plane that contains t hat and n hat is often called the osculating plane. The plane containing b hat and n hat is called the normal plane. The vector orthogonal to the normal plane is t hat, and the rectifying plane is this other plane. It's the plane containing b hat and t hat and perpendicular to n. I'm so sorry. So I've got this little moving reference frame. It goes with me everywhere I go. It's the world according to the particle. It's what traveling along this curve feels like. I'm turning in this direction. I'm going in this direction. And if I'm standing upright, or sitting upright as I'm traveling along this curve, this is the direction that my torso heads. All right, so now let's talk about what happens when this thing moves. When we're moving along the curve, the entire reference frame moves. That means we've got a change in t, so it's going to be represented by the derivative of t with respect to time. We also have a change in n as we travel along the curve, and a change in b as we travel along the curve. The differential equations that describe those changes are called the Frenet-Serrat equations. So we're going to look at those now. So now suppose we're trying to find an equation for t hat, or t hat prime, excuse me. Well, we already know that the unit vector, or the unit normal vector, the principal unit normal, is t hat prime divided by the magnitude of t hat prime. So if I solve that for t hat prime, I get t hat prime, and that's a derivative with respect to time, is the magnitude of t hat prime times the unit normal. So this is telling me that t hat prime and the unit normal are perpendicular to each other, which is something that we've already discussed. If this is the direction that I'm going, and I'm turning in this direction, so that's t hat prime, the unit normal is the vector that is parallel to t hat prime, that is exactly 1 unit long. So we just take that and we divide it by its magnitude. So now we're solving for this and we're thinking of it differently. I'm thinking, okay, well, how do I describe this rate of change? Well, according to this rearrangement of this equation, the rate of change in t hat is just this constant times n hat. Now let's break this constant down a little bit, and let's break this derivative of t hat with respect to time down a little bit as well. So I've got the derivative of t hat with respect to t. Now, according to the chain rule, instead of calling this the derivative of t hat with respect to t, I could call it the derivative of t hat with respect to a small change in length along the curve. So we're traveling along the curve through some arc of distance or length s. According to the chain rule, the derivative of t hat with respect to t is the derivative of t hat with respect to arc length times the derivative of arc length with respect to t, or arc length with respect to time. Now remember, we could think of this as length if we're thinking geometrically, or we can also think of it as distance traveled along the curve if we're thinking of r as our position vector. After some time t, we've traveled this distance s of t. So I can break this down a little bit. I can break it down even further. This is instantaneous change in distance with respect to time. We've talked about that before. That is the definition of speed. It's not change in displacement with respect to time. That's r prime. No, this is a scalar function. This is change in distance with respect to time. So that's speed. I'm going to write that first. And this ds dt, t ds, change in the unit tangent with respect to arc length, and then we're also taking the magnitude of that. Well, that's the definition of curvature. And we represent that by a capital letter kappa. So the change in t hat with respect to time is given by this, or if you're comfortable with the Greek letter nu, that's nu times kappa times n hat. Now, I could break this down using the chain rule in the same way that I broke that down. So sometimes when you're looking at these equations, you'll have the version that involves the derivative of t hat with respect to time. So here's one of them. So derivative of t hat with respect to time, so that's how this is changing, is speed times curvature times n hat. So this is parallel to n hat like we see in the picture. Or sometimes you'll see all of this written in terms of arc length. According to the chain rule, the derivative of t hat with respect to time is the same as the derivative of t hat with respect to arc length times the derivative of arc length with respect to time, or the derivative of t hat with respect to distance traveled along the curve times the rate of change of distance traveled along the curve. Actually, I'm going to use the letter nu from now on, but remember, nu is just the magnitude of velocity, which is speed. Well, this is also speed. So if I divide both sides of this equation by speed, that's gone, that's gone, that's gone, and that's gone. Oh, I'm sorry, that abusive notation. Divide this side by speed, divide this side by speed. Wow, I'm not feeling so well. I'm sorry about this, guys. Have to make this video again when I'm feeling a little better. I've got the derivative of t hat with respect to arc length is equal to the curvature times n hat. So as we travel along the curve, this is changing at a rate that's proportional to the current unit normal vector. This is the rate of change of t hat is the curvature times n hat. So we've got one version of this equation, derivatives with respect to t, it has a speed in it. Or you could break that down using the chain rule. When you do, it ends up being the derivative of t hat with respect to length along the curve times speed. We can divide the speeds out and we get this version. So this is just in general. This is one of our equations. And we're going to fill this in, so I'm leaving space for other equations as well. Or if speed is equal to 1, people often say, or if we want to get rid of the speed in this equation, we have the derivative of t hat with respect to arc length is curvature times the unit normal. Now this is completely independent of time. This is not talking about motion at all. This is talking about the geometry of the curve. So how does our unit tangent change as we move along the length of the curve? Well, it turns out to be this curvature times the unit normal. Now let's think about it. If this is our frame, if t hat's going this way and we're turning this way, and these constantly stay at a 90-degree angle to each other, as t hat moves this way, n hat is going to have to move backwards to compensate. So the rate of change, or the derivative of n hat prime, is going to have to go this way. Now you might say to yourself, how do you know, Ms. Townsend? How do you know that that's meeting that at a 90-degree angle? Well, we know that for the same reason that we know that t hat is meeting its derivative at a 90-degree angle. This vector is always 1 unit long, and if a vector is always 1 unit long, it's always orthogonal to its derivative. So is this one. So it's orthogonal to its derivative. So if there's some kind of curvature, if we are curving as we move along the curve is not just a straight line. That curvature that's greater than 0, curvature is always greater than or equal to 0, is causing the unit tangent to turn toward the unit normal, and we're just turning to the left, and the whole frame is going to turn like this. I've made a little model of a Frenet frame. I made these in class the other day. Okay, so here's my frame. Now b hat is pointing up. So when I look at this picture, this is the same as this picture. Here's my t hat. Here's the derivative of t hat. Here's n hat. There's its derivative, provided that the binormal is staying exactly the same. So b hat is just pointing straight up, and it's not moving for right now. If b hat is constant, this is what we would see. And according to the right-hand rule, t hat cross n hat is going out of the page. So b hat is right there. It's pointing straight out at us, just like it is in this picture. There's my b hat, and it's sort of coming out at us. Now, okay, so now we've got this frame. If the curvature is positive, we're moving along the curve, and the curvature is positive, well then t hat is sort of chasing n hat. And as t hat moves this way, n hat moves this way. Now whatever rate that t hat is chasing n hat, that's the same rate that n hat is moving away from t hat. Reminds me of like very unhealthy relationships, dating, something like that. You've got one chasing the other. This one just will not leave this one alone, and this one just keeps going, trying to go in the opposite direction. So that's the relationship between t hat and n hat. If curvature is positive, the unit tangent is moving towards n hat, and the whole frame is turning like this. And this is assuming that our binormal is constant. So we're just moving left and right, and because of the right-handed orientation of our system, we're only ever going to turn to the left. The unit normal is always going to be the left of us, because this is our right hand pointing out, this is our left hand. If we had to turn to the right, the whole system would flip over. B hat would be going into the page, it would not be coming out at us. So we can turn this way, but then the whole system flips. So relative to you, from the perspective of a particle traveling along this path, you're always turning left. So we're turning to the left with curvature kappa. And this plane down here, remember we called this the oscillating plane. So we're going to say that the curvature k is the rotation rate of the entire frame around this vector b hat. So b hat we're assuming is fixed. Now I know it doesn't feel fixed because you're moving along the length of the curve the whole time, but if you were to draw all three of these vectors with their initial points at the origin and then let time go on, but not force them to move along the curve, if that b hat were just pointing straight up the whole time, all you would see is curvature. You'd see t hat and n hat moving back and forth in a relationship like this. It reminds me a little bit of bumper cars. You know, bumper cars, you have that that axis that goes from your bumper car all the way to the ceiling. All you're doing is turning left and right. You're not turning out of that plane though, like you're kind of stuck in the plane the car is in, so you can turn, just keep turning to the left. Okay. So T hat is chasing N hat at this rate, and meanwhile N hat is trying to get away from T hat at this opposite rate, or at the same rate, but in the opposite direction. Notice that T hat prime and N point in the same direction, and I've got a constant times N equals T hat prime. So what that tells me is when curvature is positive, these guys are going in the same direction. Now, because the rate of change of this vector is going to be equal to the rate of change of that vector, N hat prime, and this is in the case when B hat is constant, just in this special case, N hat prime is going to have the same rotation rate, but it's going the opposite way. Look at the relationship between N hat prime and T hat. In this picture, which is only the case when B hat is constant, so B is just pointing straight up at us and it's not moving. This unit normal vector's derivative, it is parallel to T hat. And the rotation rate of N hat as it moves away from T hat is going to be the opposite of the rotation rate over here. So N hat prime is a negative of the speed times curvature times T hat. So you see the inverse relationship between those two derivatives. This one has that positive constant and this one has the negative constant. Now I could simplify this equation as well. The derivative of n with respect to t is the derivative of n with respect to s times the derivative of s with respect to t. So I can change all of these derivatives with respect to t into derivatives with respect to s times speed. So if I make this the derivative of n with respect to s times speed, and I cancel the speeds from both sides, I get this equation. The derivative of n with respect to s is negative of the curvature times t hat. So you can see from this equation that has no speed involved that these are the rotation rates of these two vectors. This one is changing at this rate. It's the curvature times the unit normal. And this one is changing at this rate. It's the negative of the curvature times the unit normal. So if curvature is positive, t hat is moving towards n hat, and they're sort of in this dance. T hat's always going to the left and it's always chasing n hat. Now that was all an assumption based on, those were all equations based on the assumption that b hat was constant. Now if b hat is not constant, if b hat's changing, I'd like to know the relationship between b hat and the other vectors in the frame. So let's derive that equation. Now remember, b hat is the cross product of t hat with n hat, so it's perpendicular to both of these. By the right hand rule, it's given by this. T hat points in one direction, n hat points in a perpendicular direction. Your thumb goes in the direction of b hat. So if this is t and that's n, my thumb goes up. Or if this is t and that's n, my thumb goes down into the page. In other directions, well, your thumb is just going to tell you which way b hat should go. So we know this is true. Now, if I want to know the derivative of this with respect to time, I can take the derivative of both sides. Now, we have not proven this fact, but it turns out that there is a product rule for cross products. It's almost identical to the product rule that you learned in Calc 1. You just have to be a little bit more careful about the order, because with cross products, order matters. T hat cross n hat and n hat cross t hat are not the same thing. They point in opposite directions. So you have to be very careful. Now from Calculus 1, the derivative of a product is the derivative of the first times the second. So I can write that down. And then we add the derivative of the second times the first. Now I can't switch the order though. And that's what I would normally do in Calc 1. I'd say derivative of the second times the first. So what instead I'm going to do is I'm going to leave the first one alone. So I'm going to say the first times the derivative of the second. Okay, now this actually simplifies quite nicely. Because of this relationship up here. The derivative of t hat with respect to time is just a constant times n hat. It turned out that constant was this times this. It was the speed times the curvature. Or I can just look at my picture. T hat prime is parallel to n hat. And what do we know about two vectors whose cross products, the cross product of the cross product of two vectors that are parallel? Well, that's going to be 0. And this is because t hat prime is parallel to n hat. And that's just using a property of cross product. Just remember, it's been a little while since we talked about that. This is the 0 vector if and only if u and v are parallel to each other. So if these guys are parallel, and they always are, this is parallel to this, then we get 0 right here. You can also remember, one thing that might help you is to remember that the magnitude of the cross product is the magnitude of the first vector times the magnitude of the second times the sine of the angle between them. If that's my u and that's my v, the angle between them is just 0. 0 degrees or 0 radians, however you want to look at it. And the sine of 0 is 0. So if they're pointing in the same direction, the magnitude of the cross product is 0, and if the magnitude of the cross product is 0, it must be the 0 vector. So this is actually the 0 vector plus this vector is just going to be this vector, because these guys are parallel to each other. And you can remember that they're parallel a number of ways. You can remember how this was defined. The unit normal was always defined to be the derivative of t hat, which points in the direction that t hat is turning. So it's, if t hat's going this way, that points that way. And then we wanted to make it 1 unit long, so we divided by a constant, its length. So by definition, this is always going to be parallel to t hat, or t hat prime, excuse me. We designed it that way. We made it parallel to t hat prime, and then we made it 1 unit long to make it the unit normal. Or you can look at this equation and see that they're parallel to each other, because t hat prime is just this constant times the normal vector. Or you can look at this picture and see that they're parallel to each other. There's t hat prime, and there's n hat. That is actually a picture that I drew because of this equation, but notice all 3 of them are telling me the same thing. N hat is a constant times t hat prime. T hat prime is a constant times n hat. Or look at my picture, n hat is a constant times t hat prime. So this is going to be 0. Alright, so now I know that the derivative of b hat with respect to t is equal to just this part. Now, if you're saying to yourself, hey, that's 0 too, because look at this picture. Here's t hat, and there's the derivative of n hat. You're absolutely right. In the case when b is constant, t hat and n hat prime are parallel to each other. So if b is constant, we'd get 0 here, and the derivative of b hat with respect to t would be 0, so that would mean b hat is a constant. So all of that is consistent. Remember, this picture is only absolutely true when curvature is positive and b hat is constant. So we're trying to think about what happens when b hat's not constant. So in that case, even though t hat prime and n hat point in the same direction, that derivative of n hat is not necessarily pointing that way. It's going to be pointing a little bit in that direction if we're curving, but it's also going to have a part in a different direction, and we'll talk about that in a little bit. So the derivative of b hat in general is the cross product of t hat with n hat prime, or the derivative of n hat with respect to t. And that tells us something. Now you might think we're just shifting symbols around and that this is not insightful at all, but it's actually very insightful. Remember what we know about the cross product. The cross product of two vectors is always perpendicular to both of them. So from this, I can infer that b hat prime, which I'm just going to denote that way now, is perpendicular or orthogonal, because we're talking about vectors, to t hat. And that's insightful because we also know b hat, our binormal, has a length of 1. And if it has a length of 1, that means that b hat must be perpendicular to the original vector b. So I'm going to be able to draw a similar picture to this, but it's going to involve the derivative of my binormal instead of derivatives of the unit normal and the unit tangent. And so what I see from this is b hat prime is perpendicular to t hat and b hat. So both of these at the same time. Let's look at our picture. Now I'm going to draw it a little bit differently. I'm going to say this is my t hat, this is my n hat, and then this is my b hat. By the right hand rule, if that's t hat and that's n hat, b hat's going to point out of the page. So that's supposed to be pointing out of the page at us, but I've drawn it at an angle so that we could see everything that was going on. Now according to this, the derivative of b hat is perpendicular to this plane, or this line and this line. Well, if it's perpendicular to this one and this one, it has to be parallel to n hat. And if it's parallel to n hat, that means the derivative of b hat must be some constant times n hat. And that constant, by convention, has a negative out front. I'm not sure of the history. I'm not really sure where that negative comes from. But this derivative of b hat turns out to be this constant. And because this is derivative with respect to time, we're going to have an extra speed factor times n hat. Or if I get rid of the speed factor, the derivative of b hat with respect to arc length is negative torsion, or negative tau times n hat. That negative is there just because of convention. And this number tau, it's a Greek letter, is called the torsion. So as b hat changes, it changes in a way that's parallel to n hat. So if this is n hat, or that's n hat, and this is the negative of n hat, the derivative of b hat is going to point this way. So maybe I should draw my b hat over here. So that's b hat, that's its derivative. Now, assuming that curvature is nearly 0, it can't be equal to 0, because if it was equal to 0, we would be on a straight line path and there would be no unit normal. But if it's approximately 0, so t hat is pointing in pretty much the same direction from time to time. It's changing slightly, it's changing just enough so that we actually have an n hat. Well, if this guy is moving this way, then this guy has to chase it. It's like a love triangle. So if N is moving towards B hat, we've got torsion. And it turns out, because of this sort of strange sign convention, when N is moving towards B, torsion is negative, not positive. And I'm not sure of the historical reasons for that sign convention, but it looks like, from what I've read, for some reason they decided torsion was positive in the opposite direction, and they just stuck with it. They didn't want to have to change all the formulas by multiplying them by -1. So we've stuck with this and just introduced this negative sign there. Okay. So N hat is moving towards B hat when torsion is negative. And if torsion is positive, N hat moves away from B hat. Okay. Now, if this is true and curvature is approximately 0, then the unit normal is chasing us. Or the unit normal is chasing B hat, at least when torsion is negative. So the derivative of N hat, if this one has a rotation rate, or if this equation has a rate of this negative torsion, the differential equation for N hat has a rotation rate that's equal to the positive torsion, because as this one's rotating, this one's going to be rotating, or as this one rotates at the same rate. So N hat is torsion times speed times B hat, or if we want to get rid of the speed, we get the derivative of the unit normal with respect to S equals torsion times B hat. But again, this is in the special case when curvature is 0. So, talked about that a little bit, but I want to make it a little bit more physically intuitive. I don't know if this is going to be very effective, but we're going to do the best we can with what we have. So here's my frame. Back here, we have what's called the normal plane. So my B hat is now this vector right here. It's pointing straight up, and there's N hat. This orange plane is my normal plane. Unit tangent is still pointing in the direction we're going, and B hat is pointing straight up at us. Now, if torsion is negative, the unit normal is moving towards the binormal. So the whole frame, it's like the oscillating plane sort of shifts. It's like it's shifting to the right. Well, I don't know if you guys can see that very well. It's like this whole thing on the bottom, the oscillating plane is rocking back and forth. So if torsion is negative, the whole frame, that oscillating plane, is going this way, or the normal plane, it's rotating, and the unit tangent is still pointing in approximately the same direction, because at this moment we're assuming curvature is negative, or curvature is approximately 0. So normal is going toward the binormal. Like, I've just lifted up the left side of the piece of paper. That's when torsion is negative. Or if the binormal is moving towards the normal, so normal is moving away from it, then torsion is positive. So let's look at this picture again. So if the torsion is negative, this guy is chasing this guy. Or let's draw it the way we traditionally do. Here's my B hat. There's my N hat. And there's my T hat. If T hat is staying pretty steady, so curvature is approximately 0, the derivative of N hat is going to point straight up. Derivative of the binormal is going to point that way. If torsion is negative, N chases B. Now this plane back here is called the normal plane. So sometimes people will say torsion is the rotation rate of the frame. So the entire Frenet frame about the unit tangent. Now sometimes some other people will say it's the rotation of the normal plane. So this plane back here that contains n hat and b hat, we're thinking of that plane as rotating and t hat is staying constant. About t hat. Okay. Now let's think about those special cases again. If b hat is constant, the only movement is happening in the same plane. If this is the direction we're going and this is the direction we're turning, we might be turning like this and turning to the left, but b hat is still continuing to point straight up. So we stay in exactly the same plane the whole time. Now, if curvature is approximately 0 and torsion is negative, the whole system, the whole Frenet frame sort of rocks to the right. The left side lifts up. If torsion is positive, it rocks to the left. The right side lifts up. Okay. That may or may not have been helpful. I hope it was helpful. But the important point that I was trying to get at there is if torsion is 0, that's the same as saying that b hat is constant. So it's not changing. It's just pointing in a single direction, and as time goes on, it continues to point in that direction. What you would have in that case is a planar experience. So you might have a curve that's doing something like this in the xy plane. Maybe you're just turning around in a circle, or like in an arc, excuse me, and you're getting farther and farther from the center. But this is planar motion. So it's just a spiral. Now, if torsion is not 0, b hat is changing. And b hat changes when you're twisting out of one plane into another. So sometimes people refer to torsion as the twist. So we might have something that looks like this. As we move up this spiral, if you were sitting in a car that was having to move up a spiral like this, you would experience sort of your torso moving in a slightly different direction as you turn, going up and up and up in that spiral. It's like going up a spiral staircase. You kind of feel it most of the time. So this is like a helix. And it wouldn't necessarily have to be a helix. It could be going outer, the radius could be increasing. But the idea is, even these curves that I've been drawing, you're in three-dimensional space and it looks like that. If you're not staying in the same plane from moment to moment, if you're changing, you're twisting out of one plane and going into another, b hat is changing. And that's when you're going to have non-zero torsion. So zero torsion, I tend to think of bumper cars. All you get to do is turn left and right, but you have to stay in the same plane, and b hat just points up. It's like that pole that extends out of your car. But if torsion is non-zero, you're twisting out of one plane and into another. Okay, so that's how we interpret that. Now we want to put everything together, everything we've talked about. So potentially you could have curvature that's positive, because curvature is greater than or equal to 0 in general, and torsion that can be any real number at the same time. If curvature is strictly positive, that means you're turning, and you're always turning left relative to our reference frame. So you're turning towards the unit normal. Because n hat is always the direction we're turning by definition. If torsion is non-zero, you're twisting out of a plane. Now we said that t hat prime is speed times curvature times n hat, and when we're on a plane curve, when torsion is 0, n hat prime is just the negative of this. Because whatever rate this is turning at the same rate, just in the opposite direction. So that's true given that torsion is 0, so given that b hat is constant. Now we also found out that the derivative of b hat is this negative speed times torsion times n hat. And if curvature is approximately 0, the unit normal is changing at a rate that's the same as this, but with an opposite sign. So it's going to be speed times torsion times b hat. Because this one is chasing this one at the same rate. Now, in general, if curvature is not 0 and torsion is non-zero, n hat prime has both of these terms. These are called the Frenet-Serrat equations. These are differential equations that describe the motion of our frame. Now, if we assume that we have unit speed, then I can get rid of all of those speeds. Or even if you don't assume unit speed, you could change these to derivatives with respect to arc length. Derivative of t hat with respect to length along the curve is curvature times n hat. Derivative of n hat with respect to length along the curve is negative curvature times t hat plus torsion times b hat. And the change in b hat, the binormal with respect to arc length, is negative torsion times n hat. So often people will refer to these as the Frenet-Serrat equations. These are also Frenet-Serrat. This is just with speed equal to 1. You might say, if speed's equal to 1, why do I need to write that as a derivative with respect to s? You're right. This is just saying that ds dt is 1. So every 1 unit of time, you move 1 unit of distance. So this is based entirely on the geometry of the curve. And this is related to motion. Like you could be going faster or slower, depending on the parameterization of that curve. Now again, it's not extremely important to me that you can state these equations, but it is extremely important to me that you understand what these quantities mean. If your curvature is greater than 0, you're turning. You're always turning to the left. T hat is turning towards n hat. If torsion is non-zero, you're twisting out of one plane and into another. Now we also talked about torsion and curvature as rotation rates. So here's my frame. T hat acts like the x-axis, n hat acts like the y-axis, and b hat acts like the z-axis. So we have a right-handed coordinate system, just like the right-handed coordinate system we draw every time we're graphing in 3D, except these are unit vectors instead of the entire real lines for the x, y, and z axes. If t hat is changing, it's always changing in a way that's parallel to n hat. If b hat is changing, it's always changing in a way that's parallel to n hat as well. Now, n hat has two parts. One part of it is going backwards, and it's determined by the curvature. If this one's changing, n hat is changing in that direction as well. But if this is changing, so if we're turning, we're going to have a little component that's parallel to t hat in the change in n hat. Now, if we're turning and we're twisting out of this plane, n hat is going to point that way, or n hat prime is going to point that way, plus a little distance in the direction of b hat. So this has two components, one in the direction of t hat, one in the direction of b hat, and then you add them together, and that's going to be the change in the unit normal. So if this one's changing and this one's changing due to the turning, this guy is going to have two components, and I can't really draw them. I'm just going to draw a vector like this. That's n hat prime. It's a linear combination of t hat and b hat, because we're turning a little bit and we're also twisting out of a plane. So that turn and that twist lead to changes in n hat. Or we can draw our pictures this way to the two special cases. If torsion is constant, or torsion is 0, which means that b hat is constant. T hat prime is parallel to n hat, and n hat prime is parallel to t hat, but it's going in the opposite direction. So this guy chases this guy, and this guy continues to move away. Or we can draw it like this. This is how I've been drawing it in class. B hat comes out of the page. T hat is over here, n hat is here. The derivative of n hat goes that way. Derivative of t hat, goes that way. If curvature is positive, this is turning towards this, or in this picture, this vector is turning toward this vector. It's like the x-axis is curving toward the y-axis. You can imagine that whole frame turning. So this is when torsion is 0. You've got motion like this. Or when torsion is not 0. But curvature is approximately constant. And we say approximately because we really need n hat to exist, and n hat doesn't exist if it's not curving, if we're not curving at all. Excuse me. In that case, n hat points up, or n hat prime points up, b hat prime points that way. And because of a strange sign convention, that torsion is negative when n is chasing b. It's positive when b is chasing n. But again, in general, we put those two pieces together. So let's talk about torsion and curvature as rotation rates. Torsion, if I look at this picture, it's the rotation rate of the entire frame about a steady t hat. So t hat is pointing out, and this normal plane back here is rotating around it, approximately. So t hat is the rotation rate, or excuse me, torsion is the rotation rate of the normal plane about t hat. And curvature is the rotation rate of this plane, which is the oscillating plane. About b hat. B hat's pointing straight up like bumper cars. You're just turning left and right. So this plane is rotating. Here, the direction we're going is staying the same. But the plane that we're in, like, it's starting to change as n hat starts to move, it starts to rotate around t hat like this. that's it.